Welcome to the lecture on analysis of rolling operations. So, in this lecture we are going to discuss about the forces which act in rolling and also the geometrical relationships, because as you know, this is the schematic of a rolling operation, and in this operation, as you see, strip will be coming of the width here. This will be the width initially, and then this will be the final width. So, as we see that there are two rolls, the O is the center of the rolls, the two rolls. So, this line is the line which is meeting the two centers. Then when the strip of this thickness, suppose we take the initial thickness as h naught. So, the strip of thickness h naught will be going inside the rolls, and then you get, if the gap between the rolls is h f, that is final height. So, certainly the strip which will be going out, it will have the final thickness as h f. So, the strip with height h naught is reduced to the height of h f. So, that is how the rolling process is carried out, and in that you have the two rolls, and as you see that this basically it is having the entry at the plane x x and the exit plane is y y. So, at this plane the roll is just touching the strip is just touching the rolls, and at this plane it is just leaving the rolls. So, that is how this rolling process is schematically presented. Now, in this case what we see is that when the basically the rolls are moving in this direction here, this is the direction of the movement of the roll. So, you know, they are moving like this, and from the bottom roll is moving like this. So, basically that helps in getting them fed into. So, this way it is moving. Now, what happens that if you look at some position here, now at this place you will have two kinds of pressure. Now, what happens that at this point you have a force component that is going in this direction, and another force component is in this direction. So, basically this is the rolling load, that the load with which it is basically pushing the material or compressing the material, and that is also known as the roll separating force, because the same way you have the reaction forces from the strip. So, that tries to separate the rolls. So, that is why this is also known as roll separating forces. So, you have this force. Another force is in this direction tangent to the roll surface, and that surface is that force is the component of the frictional force. So, that is basically that is the frictional force F here, because there is a movement of the two surface. Now, there when they are meeting, so at that time you have the friction force generated, and that goes along the tangent direction. So, once the rolls touch at this point, then this force is generated. You have F here and P here in this radial direction. So, you have one radial direction, one is tangential direction, and that radial direction talks about that force which is basically squeezing the material or compressing the material. Now, what happens that when it is touching this point, in that case basically you have a force and the frictional force basically. So, the frictional force will be acting, and that because of the frictional force here. So, if you look at this, rolling load force which is acting in this direction, it has a component in the negative direction this way. So, if you try to understand like this, so if you have, suppose you have one roll and you have, so this will be your, and you have another roll like this. Now, what happens, suppose you have one strip coming like this. Now, what happens that if this is the radius, now when, so you have this strip of larger thickness initially, and then you have the strip of smaller thickness going out. Now, in this case what we have seen that this basically this point, suppose this is a point O. So, again you will have this as O. So, this angle is known as angle of bite, as we have discussed earlier in the lecture, that this is known as angle of bite. Now, the thing is that when it is touching this point or at any point, suppose you come to any point. Now, at this point basically, as you suppose you see this point. Now, this point if you take as suppose A. So, in this case what happens, you have a force in the radial direction, and that is P radial. So, that will be the rolling load basically, that basically is the force which basically is pressing the material. Now, if you look at this, it's vertical, it has a vertical component in the downward direction, and it has a horizontal component in the negative direction. So, this way. So, basically roll if tries to go into it. Now, this roll, so if suppose you are talking about this point, at this point when it touches, you will have a PR acting in this direction, whose one part is in the vertical downward direction, which is the compressive force. Another component is in the in this direction. Now, this direction will try to inhibit the roll go into the strip go into the in between the roll gap. So, what happens at this point, there is another force, or at this point if you look at in generalized way, you have another force which is acting F. So, even if you look at this point also, so you have another force which is acting in the tangential direction, and this direction is basically opposite to the movement. So, that is why this direction is the direction of the frictional force, and because of this frictional force the roll is able to go into it. So, what we see is at this point you have initially because of the friction itself, if the friction is less it will not be able to go. So, you must have the coefficient of friction at the surface or at the in between the roll and the strip. If there is no friction, it cannot go inside, there will be, so that it will be slipping here itself, it will be rotating. So, coefficient of friction or friction is required for this strip to go in between the rolls. Now, what we see is that if you look at, here B is the width of the strip. If suppose we take B as width of strip, you take this height, initial height as h naught, and this height as you can take as h final. Similarly, it will be moving with velocity v naught here, and it will be moving with velocity v f here. This has a radius of r, roll has radius r. So, capital R is roll radius. If you look at the h naught and hf, initial and final sheet thickness or height, you can say. So, this is initial or final means before rolling and after rolling. So, that is your h naught and hf. Similarly, you have v naught and vf. So, that is the velocity of the strip before and after the rolling. So, what we see is that in this place, what we see that when the strip is touching here, because of the frictional forces, it is able to go into it. Now, if the B is constant, suppose the width of the strip is remaining constant. So, basically you are and since the constancy of volume will be applied in case of plastic deformation. So, in that case because of that the element which is vertical, which will be in the vertical shape itself. So, in that case this condition will be applied, B H naught V naught as B of H f V f. So, this way this condition needs to be satisfied. Now, B basically B we have assumed as constant in that case. Now, in that case that using constancy of volume condition, that will be the case. So, B will cancel. What you see is H naught V naught equal to H f V f. So, what we see that since H naught is more than H f, because in rolling your purpose is to reduce the thickness. So, since H naught is reduced to than H f, so it seems V f will be more than V naught, as H f is less than H naught. It means now what is this velocity? So, this is velocity of the strip basically. Now, the thing is that if, so it means the roll at this point when it is touching and trying to move, that time roll has certain velocity. Now, what happens? This means that at certain point this will have, so if there is no slipping, you will get a point where basically you have the velocity of the strip in between V f and V naught, and that will be equal to the velocity of the roll, and this point, that point will be basically somewhere here, and this is known as a neutral point. So, that point where the strip velocity and the roll velocity are equal, that is known as the neutral point, and basically it is a plane. So, you can we call it as a point, but it is a plane where basically the velocity of roll and the velocity of seat both are taken as constant. Now, what will be the roll pressure? So, if you try to see the value of the roll pressure, before that we have to see that what you have to find. Now, before that you must know that what will be the roll pressure basically. Now, there are terms like specific roll pressure. So, specific roll pressure means roll pressure divided by contact area. So, the contact area, this is the projected this projected length of the arc L p. So, this length we call it as L p. So, this length is basically the length L p. Now, what happens that in this case what we see that you have the width of this strip is the 1, and this is the area, this is the chord area, arc area. So, this will be the arc, this arc basically multiplied by the width, that will be the area of contact, and this area of contact, which is when it is divided by the roll pressure, roll load, that will give you the roll pressure. So, specific roll pressure will be the roll pressure divided by contact area. Now, how to find this contact area? So, for that again we have to see that how can we find the roll contact area. So, for that, if suppose what we see is, suppose you want to find the roll contact area, in that case you have this, and this is your so suppose this is the strip and this is going from here. So, suppose this is the final sheet. Now, in this case you have this as the final, this as the radius. So, now this is r. Now, what we do is Now, in this case you just make it this way, and you have to make a horizontal line. So, what we see is if you further extend it, and this is the 2R. So, in that case we have to have a drawing where, if suppose this is, so just let us rub it. Now, if you try to see that this is the final point which is on the periphery of this roll, in that case if you try to match it. Now, what we see is that in this you have to do the nomenclature. So, suppose this is the P, this is Q, this is R anyway, this is suppose A, this is B, and this is O. Now, what we see is that this is a horizontal line, so this triangle and this triangle, so like triangle QBA and triangle QPA, both are basically similar. So, this is a horizontal line. So, basically this is 90 degree. So, here similarly this is the 90 degree, and so this triangle QBA and triangle QPA are similar. So, in this way what you can find by using the similarity condition. So, if you look at this triangle QAB and QPA are similar. So, QAB is similar to triangle QPA. So, what will happen? QA upon AB. So, QA is opposite to this angle. So, this angle is 90 again. It will be AP divided by, and AB is this angle. So, this angle opposite is same as this. So, that will be QA. So, that is by similarity of the two triangles QBA and QPB, QAB and QPA. Okay. So, what we see is QA square is AB into AP. So, this is what you get from this. Now, so what we see is you can find QB. Now, if you try to find QB, QB will be equal to QA square minus AB square. So, it will be under root QA square and minus AB square. So, QA square is, you can write as AB into AP and then minus AB square. Now, if you look at this figure AB and AP. So, AB is nothing but, if you see this is the height h naught and this is the height h f. So, AB is nothing but h naught minus h f by 2, and so this is AB, and AP is the 2 times the radius, so 2r. So, neglecting this term, basically if you neglect this term, because this will be again further small, if h naught minus h f is very small, in that case this term may be neglected and you can take it as 2 r multiplied by h naught minus h f by 2. So, it will be r naught h naught minus r multiplied by h naught minus h f. So, sometimes we also write it as under root r delta h. So, this is how this contact area. So, in that case basically if you take this area, this is same, you can take, if that is very small, in that case this can be taken as equal to this or so. So, in that case this will be your roll contact area. So, this roll contact area multiplied by the specific roll pressure give you roll load, or roll load divided by this roll contact area, that gives you basically the so this will be the length basically, this is the length, and then you are multiplying it with B. So, this is roll contact length, and then roll contact area will be B times LP. So, you write this as length of this projected area of the arc, that as R delta H. Now, if you want to find the roll load, or you want to find a specific roll pressure, in that case B times LP. So, where that way you have to multiply the pressure and you get the roll load. So, that is how the roll load is calculated. So, what we see is that we have seen that you can calculate this roll load or roll specific pressure depending upon the area of contact, and area of contact will be basically B times this roll contact area. So, this is the contact length multiplied by the B, that will be giving you that final pressure. So, P will be roll load divided by B into LP. So, this is how you find the roll pressure. Now, further if you look at the roll pressure value will be basically varying, and if you look at the roll pressure value, it will vary like this. So, basically this is a roll pressure, and this is your entrance, and this is exit. So, in this case this maximum is basically achieved near the neutral point. So, that is how that is the significance further of the neutral point. Further, we discussed that you have the two kind of forces. One force is trying to will have the effect like it will try to try not to allow this strip go into it. Another force is basically the force, that component of the frictional force, which basically or the force which is here the tangential force, that is. So, this force, its component in the x direction, it will try to put it inside the rolls. So, basically what happens, you have if you look at the horizontal component here, you will have, this is the PR. So, you have this is as alpha. Now, if you look at this, its horizontal component is PR cos alpha, and similarly F has the horizontal component as F sin alpha. So, PR cos alpha, so no, PR cos alpha will be here. So, it will be PR sin alpha. So, its horizontal component will be PR sin alpha here, and F will have F cos alpha in this side, and both have to balance. In fact, F cos alpha have to be more, so that the metal goes into it. So, in the limiting condition, this PR then sin alpha has to be equal to F cos alpha. So, you have F cos alpha has to be PR sin alpha. Now, so tan alpha will be F by PR. That is what you see from here. If you look at this point, this point is, suppose here you have F in this direction and you have PR in this direction. So, you will have F by PR as tan alpha. Now, the F will be basically mu PR. So, F actually is, as F is mu PR, because you will have the coefficient of friction at the metal interface. So, you will have mu as, so mu will be F by PR. So, that is why you get mu as 10 alpha. So, basically what happens that workpiece cannot be drawn into the roll if the tangent of the contact angle will exceed this coefficient of friction. So, that gives you a limiting case, that when the roll will not be going inside, I mean the strip will not be going inside the rolls, what that component must exceed, so that this strip will go in between the rolls. So, that is why that is the limiting condition, where when the roll cannot enter the in between the strip cannot enter in between the rolls. You can also find the delta H maximum, and basically if you find the expression for 10 alpha. So, 10 alpha will be basically the LP and divided by this R minus delta H by 2. So, that is what, if you look at this 10 alpha, you see that 10 alpha will be you will have LP divided by R minus delta H by 2, because you will have this projected length. So, 10 alpha, if you look at, you will have this length, that is your LP, and then this height. So, it will be basically this is your hole is R, and this height is delta H by 2. So, HF H naught minus HF divided by 2. Now, if you look at, LP is R delta H under root, and then divided by, so this can approximately be taken as basically LP is, so that will be under root R delta H. So, that way delta H by R will come. So, that will be approximately oblique of delta H by R. So, if you look at that, 10 alpha has to be mu. So, if you take that value, mu square will be delta H by R, and delta H maximum can be that is why you get mu square by mu square into R. So, since this is mu, so delta H maximum, this will be basically delta H maximum will be R square into mu. So, this you can say how you can find that maximum of the reduction depending upon the radius R and the mu. So, that can be basically found out. So, these are the points. So, now what we see is rolling load that we have already discussed, roll contact area is already discussed, friction. So, direction of friction we have already seen, that direction of friction force will be changing at the neutral point. Throat of the roll, when the horizontal component of frictional force tend to push the strip in between the rolls, the horizontal component of rolling load tends to oppose it. So, that is what we have already discussed, that this rolling load, its horizontal component is trying to oppose this, and for the workpiece to enter between the rolls, the component of frictional force must exceed or in limiting case be equal. Now, before that we have further to see that what are the other parameters, basically how we calculate the rolling load in case of the rolling, that we will see. So, what are the main parameters in the rolling? Basically roll dia is there, then deformation resistance of the material. So, that is basically influenced by the metallurgy and temperature, also strain rates. So, these are the parameters in the case of rolling. Friction between roll and the strip surface is also one important parameter, and as we have seen that rolling load will be basically the roll pressure and multiplied by the area of contact. So, if we neglect the friction in that case, so your pressure becomes the yield stress of the material. So, in that case the you can find the roll load, and roll load will be PB P multiplied by, so that is pressure. So, in that case, as you neglecting the friction, so if you neglect the friction, in that case the pressure becomes the yield stress. So, in that case the raw load will be pressure multiplied by B times LP. And again, as you know, you have B as the LP as under root R dH, R delta H, and P in that case the plane strain yield stress value. In that case, you can take it as sigma naught prime and R delta H. So, this is plane strain yield stress value. So, that becomes basically in such situations you have to assume, you have to take this expression into account, because in this case we have, this is a case of plane strain, because we have fixed the B. So, in one direction the strain is negligible, it is 0. So, we have, since we have fixed that, in that case this sigma naught prime, that will be the plane strain yield stress value, and you can find this raw load as P equal to small p b LP, and that will be sigma naught prime, and B in, and that will be LP. Already we have discovered the relationship for this. Now, even when we have friction, in that case we will discuss in future, I mean in the coming lectures about the forging. So, in that case when we have friction and then when we apply the load, the compressive load, in that friction heel is generated and we can find the load in that case. So, in that case using the mean concept, mean deformation pressure, you can find the value of the mean deformation pressure, and mean deformation pressure by sigma naught prime. This is the case when there is friction. So, that basically we want to calculate. Now, in this case you can find it will be equal to 1 by q e raised to the power q minus 1. So, q basically depends upon the contact, where the at which contact the die is in contact with the strip, and basically that will be mu into LP divided by H prime, H bar. So, q is mu LP divided by H bar. So, that is mean height, and LP, as you know, that this is the contact length, and this will be mu. So, H will be mean thickness between the entry and the exit. H bar will be that mean thickness between entry and the exit. So, what we see is, now in this case if you find the P, so what we get is P will be, so what we have got this expression, P will be basically P bar and then multiplied by BLP. Now, P bar value we will get from here. So, that will be sigma naught prime, and then you will have in that case you get the 2 by root 3, and then you get the mean value of the stress. So, this will be 2 by root 3 sigma naught. So, that will be mean value. Then further you have these values 1 by q into e raised to the power q minus 1. So, 1 by q e raised to the power q minus 1, and then further you have the value this b into under root r delta h. So, this is how you find the value of the load. In this case, this 2 by root 3 factor is coming because rolling is in the plane stress situation, and flow stress should be the flow stress in the plane strain. So, that is why if we recall our previous calculations, previous findings, we get this expression, and you can find the values, because once we know this sigma naught bar, then we can find. So, this is average stress value. So, once you know that, then finally you can find this rolling load. So, this is how the value of this rolling load can be found out. Now, if you look at this, what we see is that here you see certain values, that P is basically dependent upon this Q and also this R delta H. So, basically what we see is it is dependent upon the radius or radius of the roll. Now, in general what it has been seen is that roll dia is important in that case. Both roll load and the length of arc both are important for the calculation of the roll load, and smaller dia rolls are basically giving you that way more effective, and they are basically stiffened, and then so that is how you apply the backup rolls to do the rolling operations. So, there is certainly a minimum gauge sheet which can be rolled. So, there is a limit upon those cases, and that is how the rolling operation has to be carried out. So, among the important parameters which influence this rolling load is that basically the rolling load as well as the length of arc both are basically decreased by because of the roll diameter. So, basically smaller dia rolls are, that is why preferred, but they are to be basically they have to be given the rigidity, and that is why you put the supporting rolls in those cases. So, this is about the rolling load calculations. You can also study the effect of hot working. So, in case of hot working you need to have you have to study about the effect of strain rate. So, in that case the strain rate, that term comes into picture, and in case of cold rolling we have seen that you have what is the maximum height of reduction possible depending upon the mu and r. So, this way you can find the calculation of rolling load and other reductions possible or so. Thank you very much.